So now you know that we can build secure communication upon shared randomness. So if Alice and Bob share completely random, identical, and secret sequences of bits, say, then they can use, for example, one-time path, which I have just described, and communicate with perfect secrecy. Now, when we need perfect randomness, there's just one obvious way. You can use quantum entanglement to distribute or establish shared randomness in two different locations. So indeed, consider situations where Alice and Bob get entangled qubits, and after a while it could be like external source that is sending one qubit to Alice and one qubit to Bob. And after a while they accumulate n pairs of entangled qubits, and say each pair is in this state omega, which is 1 over square root of 2, 0, 0 plus 1, 1. So then you can see that due to this entanglement, if Alice and Bob perform measurements in the computational basis, which is essentially the Z basis, right? So they measure sigma Z operator. That's the observable they are going to measure. Then the outcomes will be perfectly correlated. So whenever you can see from this expression here that they will register with probability half outcome 0, 0, and with probability half outcome 1, 1. In fact, when you use observable Z, we relabel the outcomes, and then outcome 0 is now called 1, and outcome 1 is now called minus 1. So those are the two eigenvalues of the Pauli operator sigma Z. It should be then quite clear that there is a perfect correlation in this particular case, and then there's also, perhaps it's worth elaborating that there's also perfect randomness here. So one way to see it, if you want to do it in a slightly more sophisticated way, of course, to some extent you can say that it's obvious from the from this expression, but you can also say that if I have this state of the two qubits, the state of each individual qubit is described by the reduced density operator, right? So I take state omega, turn it into density operator, that it is the projector on state omega, and then I can trace over this qubit on the Alice side. And when you do this, it's a very simple calculations which you should be able to do now. You get the maximally mixed state. That means that the reduced density operator is proportional to the identity. It's half the identity, and the same holds if you trace over Bob's qubit. So that gives you also the identity. So then clearly if this is sort of the density operator associated with each qubit, and if you want to know what is the value of the average value of observable Z, then of course it is trace Z times half identity, which is equal to half trace Z, and you know that the Pauli operators have 0 trace. So that means that the outcome +1 and -1 appears with the same probability. So in fact, that perfect randomness, the fact that they really appear with equal probabilities, those two different outcomes, 0, 1, or +1 or -1, it is actually quite profound. It's not only that it comes out nicely from the formulas of quantum theory, but there is amazing sort of symbiotic coexistence here of quantum theory and relativity. It turns out that if it were not the case for this kind of entanglement, where you can generate a correlation, if it were not the case that the local subsystems give you a completely random outcomes, then you would be able to construct devices that would actually allow for instantaneous communication. So it's in this case, Bob performing the measurement on his qubit would be able to transfer some information to Alice, which is something that we don't want to have. I mean, somehow, at least, we would like the relativity and quantum physics sort of to have this peaceful coexistence, and they do have, surprisingly, even though we derive them from somewhat different principles. Anyway, so here we have a scenario where Alice and Bob, as long as they share a large number of entangled qubits, they can generate identical outcomes. So if they just simply measure each qubit in the Z basis, so the outcomes would be identical. So it's going to be, say, 0, 0, 1, and whenever Alice has 0, Bob has 0, 0, 1, or using the Z labeling, that could be +1, +1, -1, +1, +1, -1. So you may say that this can then form a cryptographic key, because those binary strings are perfectly correlated, and we know that they are truly random. This randomness is very important for cryptographic purposes, because it allows you to mask any statistical distributions of a natural language in the message. Well, that's true. We satisfy the property of randomness, perfect randomness, and we managed to somehow make sure that those two random sequences are identical. The problem that we have with this scheme is that it is not secure. You can easily imagine situations where an adversary, an eavesdropper, essentially gives Alice and Bob either state 0, 0 or state 1, 1 with equal probability. So you may just imagine that somewhere here, instead of entanglement, you have your eavesdropper that we called Eve, of course. And Eve will just choose and distribute either state with equal probability. Will just send 0, 0 or 1, 1 to Alice and Bob. And if Alice and Bob only measure Z observable, they will not be able to tell the difference between the two. And Eve, of course, knows which value was sent to Alice and Bob. So this system obviously is not secure, and we have to work harder. We have to take this idea and do something to it so that we just exclude Eve from the game. So that's our next step.